Section 3-9 is on the derivatives of exponential and logarithmic functions. The objective of this section is given an exponential or logarithmic function, find the derivative function. So if you go back and look at the rules that we already know for finding derivatives, we've actually got quite a few. We know the rule for the derivative of a power function called power rule, the rule for the derivative of the sum of functions, the rule for the derivative of the constant times a function, the rule for the derivative of the constant function. We've also talked about the rule for the derivative of sine and cosine, and we also talked about the rule for the derivative of a composite function called chain rule. So we have quite a few rules at this point in time that we know. We're just going to add to that list of rules that we know. All right, so let's get started with the exponential function. And actually, we're going to look at an example here to help illustrate this. We're going to take kind of a graphical approach to explaining why the derivative is what it is. And then we're going to look a little bit further into this in Chapter 4. So the example here on page 115 is looking at the function f of x is equal to 2 to the x, and we want to find out what f prime of x is equal to. So to do that, we're going to go back to our formal definition of a derivative function. So that is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. There's our formal definition, and as is usual, the first step we do here is substitute in for function f. So it's the limit as h goes to 0. And f of x plus h means I'm going to take an x plus h and substitute it into function f there. So it's going to be 2 raised to the x plus h. 2 raised to the x plus h. Minus f of x, which is 2 to the x. And that's all divided by h. Okay, now we have a property that deals with exponents that we can use here to help us simplify this a little bit. If I have 2 to the x plus h, I can rewrite that in the following way. So I've got the limit as h goes to 0. So that first thing that's in the numerator is 2 to the x plus h. And I can write that as 2 to the x times 2 to the h. Usually we use that rule in the other direction, that we start out with something like this, 2 to the x times 2 to the h. And we can combine those because they have like bases. And when we do that, we add the exponent. So it becomes 2 to the x plus h. But we're going to just split it back apart here. And then minus the 2 to the x all over h. So now you can see what we end up with in the numerator is 2 terms, and each term has a 2 to the x in it. So we're going to factor out that 2 to the x. So it's the limit as h goes to 0 of 2 to the x. I'm going to just go ahead and pull that all the way outside of the fraction here. 2 to the x times the quantity 2 to the h is what's left in the first term in the numerator. And when I factor out or divide out the 2 to the x in the second term there, it's left with a 1 all over h. And then what I have here is the limit of a product. And so we have a rule that says, a rule for our limits that says the limit of a product is equal to the product of the limits. That's one of our limit theorems. So this is the limit as h goes to 0 of 2 to the x times the limit as h goes to 0 of 2 to the h minus 1 over h. And in the first limit there is no h's in there. The limit as h goes to 0 of 2 to the x, there's no h's. In essence, it's kind of like a constant. So that limit is just equal to 2 to the x times the limit as h goes to 0 of 2 to the h minus 1 all over h. So the question here becomes, what is that limit there equal to? What is this guy right here equal to? It appears like the derivative involves, the derivative that is of 2 to the x, involves the original function 2 to the x. Right here is the original function. And we're going to multiply that by some limit. Now, a limit, of course, is going to give us some number here. So this is some constant. And we need to find out what that unknown constant is and figure out what it is and use it now for our rule for derivatives. So we're going to analyze that limit here. And we're going to do it numerically, like I said. You could do it graphically as well by graphing it, but I think a numerical approach is going to be a better way for us to look at it. We'll just plug this into our calculator. So under your y equals menu, let's put in 2 to the x instead of 2 to the h minus 1. And we're going to divide that by x instead of h. And again, we're going to do it numerically here, so I'm just going to go right to the table. And it's the limit as h goes to 0, but we've replaced h's, of course, with x, so it's the limit as x goes to 0. So we just want to find out what's happening as we get closer and closer to 0. So I'm going to just set this up into ask mode, and I'll plug in smaller and smaller values on the left side and the right side of 0 and see what happens there. Okay, so let's go to our table, and let's start on the left side of 0. So if it's negative 0.1, I guess is where we'll start. You get 0.669, and a negative 0.01. Zooming in a little bit further, we get 0.6907. Let's go a little bit further here, negative 0.001. And we get 0.692, 0.693, I guess that rounds up to. Okay? And on the other side, if I plug in a 0.1, we'll start a little bit further to the right here. We get 0.717. Okay, let's get a little bit closer on the right side, so we'll make it 0.01, 0.695. We'll get a little bit closer, 0.001, 0.693. So it looks like this is approaching a value somewhere around 0.693. From the left side, it was actually getting closer to 0.6929. Here it's 0.6933, so it's somewhere around 0.69. And we can keep getting closer and closer to the from the left and right side and seeing what value it's approaching, but it definitely looks like it's approaching a value somewhere around 0.69 something. And so then the next question is, well, what is 0.69 in respect to this problem here? Okay, and the key for us to recognize here, although it might take us a little bit of time to recognize that number, it's not quite as easily to recognize 0.69 and recognize what it's equal to, but it turns out that if we calculate the natural log of 2, which is the base of our exponential function that we started out with, that turns out to be 0.693. It is not a coincidence that that's the number that we're approaching. It turns out then that this limit here that we've outlined in red is actually equal to the natural log of 2. So it turns out this is equal to 2 to the x times the natural log of 2. So in other words, to find the derivative of an exponential function, you end up with the same exponential function you started with, 2 to the x, and you multiply it by this constant of natural log of 2. Okay, notice that this is an exponential function. It's not a power function. You can't try to use power rule on this thing and find the derivative. You have to have a rule for exponential functions in order to define the derivative of it, and that's what we've just come up with here. This shouldn't be too strange to us that we're multiplying by some constant, because that's kind of what we do with power function. Remember, power functions, when we take the derivative of a power function using power rule, you end up bringing the exponent out front. So you're multiplying by a new constant out front, the exponent. And actually, you multiply by not quite the same function you started with, but rather a degree less than 1, or 1 less than what it was. Because we take and multiply by x raised to the n minus 1. Okay? So to some extent, this kind of looks similar to that rule, but obviously it's not quite the same. All right, so here are our derivatives of the exponential functions. We'll start with the one that actually turns out to be the nicest of them, and that's a base e. The rule for the derivative of e to the x, if f of x is equal to e to the x, then f prime of x turns out to be e to the x times the natural log of e, but natural log of e is 1. So it turns out the derivative is just e to the x. That's really nice. Now the one that we just worked with there, we just saw that if f of x is equal to b to the x, in our case b was equal to 2, then f prime of x is equal to the natural log of the base, that b value, times b to the x. There is our rule for the derivative of exponential functions. So now we've added a new rule to our set of derivative properties that we know. We now know how to take the derivative of exponential functions. So let's see if we can do that here. Take a look at example 1 there. And example 1 says, find f prime of x if f of x is equal to this. So f of x is equal to e to the cosine of x. And it says, confirm the answer by graphing the algebraic and numerical derivatives on the same screen. We can do that and just check to make sure that we get the same result. That's one way to verify that your derivative is correct. So we want to find f prime of x. Well, the first thing we got to recognize here is that you've actually got a composite function. The inside function is the cosine of x, and the outside function here is this base e. So it's really e raised to the cosine of x. So we first take the cosine of x, and then you exponentiate that to base e. So there's our composite function. We have to follow chain rule then to take this derivative. So follow the rule for chain rule. Chain rule says take the derivative of the outside function. So we have e to some power is our outside function. The rule we just found out, that base e turns out to be a really nice function to take the derivative of because it turns out to be its own derivative. So turns out the derivative of the outside function is just e raised to some power. That's the derivative of the outside. Chain rule says then you evaluate or you substitute in the inside function. For us, the inside function is cosine of x. Notice that you start out with the exact same thing that you started with when you find the derivative. The third step of chain rule now is to multiply by the derivative of the inside. Derivative of cosine is a negative sine of x. And I guess to rewrite that, we'd probably put the negative out front. Negative e to the cosine of x times sine of x. And there is our derivative function. All right. Let's take a look at the second type of function we wanted to look at, which was logarithmic functions. Now, for a logarithmic function, there's actually several properties here that we need to kind of refresh our memory of here probably. These are listed in your book there on page 118. The first thing is the definition of a logarithm. Okay, remember the relationship between exponential functions and logarithms is that they are inverses of each other, and we see that from the definition here. Here's the definition of a logarithm. We say that a is equal to log base b of c if and only if the following is true, that b raised to the a power is equal to c. So I can always take a logarithm and rewrite it as an exponential, or vice versa. I can take that exponential and rewrite it as a logarithm. And we use that property to help us solve, depending on what we're trying to do, we use it to help us solve for a particular unknown. If we start out with an exponential function like we have at the end here, b to the a equals c, and you're trying to solve for a, then we rewrite it as a equals log base b of c. On the other hand, if you have a equals log base b of c and you're trying to solve for c, then we rewrite that as b to the a equals c, like we have at the end. So depending on whether you want to solve for a or for c, depends on how you write that. But you can always take a logarithm and rewrite it as an exponential, and vice versa. Take the exponential and rewrite it as a logarithm. So there's our definition. And the thing to remember here with a logarithm is realize that anytime you're finding a logarithm, you're finding an exponent. Okay? And you can see that here with the fact that whenever I calculate this log, I'm getting this value of a as a result. The log of some quantity gives me a. And the a value over here in the exponential form is the exponent. So that's why we say when you calculate a log, you're really finding an exponent, and the exponent that you're finding is the exponent in this little equation right here. Okay? So let's look at the logarithm properties. And the first property there is the property for the log of a power. We actually use this quite often when we want to solve for something that's in the exponent. We take the log of both sides. We use logarithms to solve that. And it's because of this property right here. If you have the log base b of c raised to the d power, that's the same as d times the log base b of c. So you can take that exponent, that d, and you can bring it out front as a coefficient in front of the logarithm. All right, take a look at the second property. This is our product property. Product property says that the log base b of c times d is equal to the log base b of c plus the log base b of d. In other words, the log of a product, c times d, is equal to the sum of these two logs that we have on the right side. Okay, log of a product is equal to the sum of the logs. And then the last property here for us is the log of a quotient. If you have log base b of c divided by d, then you can rewrite that as the log base b of c minus the log base b of d. So again, the way we read that is the log of a quotient is equal to the difference of the logs. Log of a quotient is equal to the difference of the logs, and the log of a product is equal to the sum of the logs. All right, so let's take a look at an example here. This is on page 118, and it says let y equal the natural log of x, which natural log of x, we'll again explore this a little bit further to see why this is the case, but turns out natural log of x is the same as log base e of x. And we want to find out what y prime is equal to. Okay? Now, in order to do that, we're going to use a little technique that's called implicit differentiation in this process. So I'll first set this up and then show you what implicit differentiation is. So I'm going to write down that y is equal to log base e of x. And I want to use the definition of logs to rewrite this. And I want to rewrite it in a form that I can use my previously proven property here for the derivative of an exponential function to find the derivative of this logarithm. So my definition of a log, if you say y is equal to log base e of x, that's the same as saying the base e raised to the y power is equal to x. Those two statements mean the exact same thing. That's just straight from the definition. And now what I want to do with this is I want to take the derivative of both sides. I want to find out what the derivative with respect to x of both sides of this equation is. Now, to do that, we use what's called implicit differentiation. Okay, we're going to talk more about implicit differentiation later on, but the reason why we call this implicit differentiation is because of the fact that this is an implicit relationship now, and we call it an implicit relationship when it's not solved for y. It's not solved for your dependent variable. The rules of differentiation, though, still apply. We still follow the same rules. We just have to remember what those rules are, or at least I'm going to point them out to you here, that if you take the derivative with respect to x of that same variable x, we get 1. On the other hand, if you take the derivative of, or derivative with respect to x of any other variable, in our problem we have y, you don't get 1, we get dy dx, or we call that y prime. Again, you can just slide that y, when you say dy dx, you can slide that y into the numerator and see why that's the case. You end up with dy dx. In fact, in that first one that we saw there, I can even illustrate that here. Let me just back up and get rid of the 1 that we had there. If I just slide the x into the numerator, you'd have dx dx. And of course, dx over dx, that's equal to 1. This is why it ends up being 1 for us. All right? So with that in mind, we should be able to take the derivative of what I see here on the left. So take the derivative with respect to x. So think of e to the y as a composite function. E is the outside function and y is the inside function. So follow chain rule. Chain rule says take the derivative of the outside function first, so that's e to some power. Second step of chain rule says substitute in the inside function, that would be y. And the third step of chain rule says we multiply that by the derivative of the inside function. That's the derivative of y. That's what we just did over here on the right. Derivative of y turns out to be y prime. We took the derivative on the left side. I need to be fair and take the derivative on the right side in order for this equation to be the same. So on the right side, when I take the derivative of x with respect to x, again, we already did that over here on the right, that's where we get 1. Now, what we are trying to find here, remember, is what y prime equals. So I want to solve this for y prime. So I'll go ahead and divide by the e to the y. I'll end up with 1 over e to the y. And there's the derivative. The only thing I don't like is the fact that I started out with a function that was defined in terms of x. Y was a function of x. And I end up with y prime as a function of y. And I'd like to have it in terms of the same variable. So let's see if we can replace e to the y with what it's equal to. If I can get rid of the y, or really the e to the y is what I'm going to do. And I can do that by just going back up to this step where we said that e to the y, based on the definition of the log, e to the y is just equal to x. So it turns out that this is equal to 1 over x. So the derivative of the natural log function, or log base e of x, turns out is equal to 1 over x. Okay? So here's that property. Just to formalize it for us, if f of x is equal to the natural log of x, then f prime of x is equal to 1 over x. Now this is for the natural log function. We'll talk further about the about logs of any other base a little later on. All right, we just want to look at natural log though for right now. All right, so let's try this in an example. Look at example 2. Example 2 says if f prime, or excuse me, find f prime of x if f of x is equal to the natural log of x cubed. And again, they say to confirm the answer by comparing values with the numerical derivative. Remember, you can use your calculator to check to see if your answer is correct. All right, come up with what you think the derivative is, and you could sketch that and sketch the numerical derivative along with it and see if they're the same. Or you could even use the table as it's suggesting here and comparing values with what we believe the derivative is versus what the numerical derivative is, and see if we get the same results. But let's first find the derivative of this thing. We're going to use the rule that we just laid out there. The first thing I got to recognize is that you've actually got a composite function here. The x cubed is the inside function, and the natural log of that is the outside function. If it helps you to put parentheses in there, you can go ahead and add parentheses. They're not necessary, but if it helps you to see that composition, then do it. So follow chain rule. So chain rule says take the derivative of the outside function. So the derivative of natural log. We just said the derivative of natural log is 1 over something. And chain rule then says you substitute in the inside function. So the inside function there is x cubed. And then we multiply that by the derivative of the inside function. That's the third step of chain rule. Derivative of x cubed is 3x squared. And we can simplify that. If I take the x squared in the numerator and cancel out with 2 of the x's that are in the denominator, I'd be left with just 1x in the denominator. In other words, this simplifies to 3 over x, or 3 times 1 over x, however you want to write that. That's one way you could find this derivative. Another way that you could find the derivative is to first use your log properties, which is very common. That your log properties are pretty nice at simplifying functions for us if we use them, and making the derivative simpler to find. Let's go back to the original function, natural log of x cubed. If you want to put it in parentheses, you can. Remember, we have a property for the log of a power that says I can rewrite this with that power written out front. So we end up with 3 times the natural log of x. And now it's the constant times a function is all I have here. So I can take the derivative of that without having to use chain rule. Derivative of the constant times a function is the constant times the derivative of the function, and derivative of natural log of x is 1 over x. We get 3 times 1 over x, or if you want to put the 3 in the numerator, we get 3 over x. Notice that's the same result we got earlier. Okay, let me demonstrate. I didn't do this with example 1. Let me just demonstrate on your calculator how we can graphically show that this is the correct derivative. If you go to your y equals menu, and we'll put in the natural log function in y1. And in y2, let's put in the n deriv function. We'll tell it to take the numerical derivative of y1. Your variable is x, and my value is x. And in y3, oops, I'm sorry, our function was x cubed here, natural log of x cubed. And in y3, let's put in what we found, or what we believe to be the derivative of 3 over x. And I'm going to change this so it sketches with that little circle there, so I can kind of trace it and see if in fact it's sketching right on top of that numerical derivative. I'm just going to sketch this in the standard window. I guess technically we could have shut off the natural log function. I don't really need to see it sketch. And we get an error. Oh, it's because of my domain here, actually. I got to change that. Let's change the domain of this function. The natural log function is only defined on the positive domain, so I can't find numerical derivatives in the negative domain. So let's change this domain. Let's go from 0.1, we'll say, to 10. Let's try that again. So there's that natural log function. Here comes in the sketch there of what we believe, or not what we believe, but the sketch of the numerical derivative. And here is what we believed, or what we came up with for our derivative algebraically. Notice that it's tracing right on top of that numerical derivative. The other way, again, you could do this is to go to your table. I'm going to start out my table at 0, and we'll have it changed by 1, we'll say, and put it into auto mode. And go to our table. Oh, whoops, of course I can't start at 0 again. Let me go back there. Let me start it out at 1. Again, it's not defined on the negative domain or at 0, so that's what the problem is there. But if I compare y2 and y3, I can see I'm getting the same results between these two. You can see that the numerical derivative, there's a slight error if you look at the output there at the very bottom. There's a slight difference there, but that's to be expected because it's just an approximation. But you can see basically we're getting the same values between the two. Okay? All right, and that is the end of this section here for us, or the first half of that section.